Okay, so now we're going to discuss the notion of connected components, starting with the discrete perspective and then sort of going to the continuous perspective. And then it's like we're going to try to establish the connection and relationship between the two of them. Okay, um, so so the notion of connectivity, if you will, is a fundamental concept that's like in topology. And so we're going to try to illustrate it's like these ideas. It's like first and foremost using the notion of graphs. Okay, so connected components. And then what we'll see, if you will, is that the graphs are then going to be extended. It's like to what we call simplicial complexes to deal with, you know, more complicated notions of connectivity in some sense. So in any case, an ongoing theme sort of in this course, right, is the interaction, if you will. It's like between discrete and continuous representations or descriptions. It's like, or spaces, right? And basically how they relate to each other. Okay, so we'll first discuss this notion of connectivity in the discrete setting, and then in a subsequent lecture we'll talk about how what the continuous analog of these ideas would be. Okay, so. So let's discuss this notion of connectivity in the discrete setting. And later we'll discuss the continuous analog. Okay. All right, and so it's like the setting. It's like for describing connectivity. It's like in the discrete sense, it's like would be. It's like the simplest example would be a graph. Okay, so let's say a little bit about graphs. So we'll first talk about abstractly what a graph is. All right, so an abstract graph is this tuple, so denoted G, is this tuple. It's like of two sets. It's like V and E, where V is the vertex set and E is the edge set. Okay. Sometimes vertices are also referred to as nodes. Okay, and E is the set of edges. Connecting the vertices. Okay. All right. So for the purposes of this discussion, it's like we're primarily going to consider what are called undirected graphs, which is to say that the edge, it's like which connects two vertices, doesn't have a direction. So you can think of them as being unidirectional. So, sorry, bidirectional if you want. Okay. So there's also the idea of directed graphs. It's like where the edge, it's like has the idea of going from one node to the other. It's like, and then it's possible that the reverse connection doesn't exist. All right, but again, for now, we're going to consider this idea of bidirected or undirected graphs. Okay, so a graph is undirected. right? If all the edges are bidirectional, okay. All right, so let's sort of try to recap for now. Usually it's like when you have vertices, it's like you typically draw them, it's like with little circles or nodes, all right? So this, it's like 4 vertices, it's like that's the set of points, it's like you want to connect. So as a preview to the idea of connectivity, right, you might say that you know, it's like these 2 points connect. To represent the fact that these 2 points are connected, you might draw an edge, it's like connecting them. Okay, so you might have something like this. All right, so that's an example, for example, of a graph, right? So you could have sort of graphs where you have cycles, right? So this is what is called a cycle. And so what we're going to do is to look at, in particular, what are called simple graphs, okay? So a graph is simple if 2 things are disallowed, right? If there are no parallel edges, and no loops. Okay, so what do I mean by a parallel edge? I mean a parallel edge is basically 2 edges, it's like which connect the same pair of nodes, right? So this would be a pair of parallel edges. So I don't want to allow that in a simple graph, right? The other thing, it's like I don't want to allow loops. So loops are basically edge which goes back to the same, which connects the node to itself, if you will. So I don't allow these 2 things, all right? So again, if you have a graph, right, so I should say an undirected graph. Graph is simple if there are, again, it's like no edges which connect the same pair of points more than once, and there are no loops which connect a node or a vertex to itself. Okay, so we say this graph is simple. Okay, and then let's sort of do a little bit of notation and say a little bit more. It's like about these kind of simple graphs. Okay, so you let n be equal to the number of vertices. Okay, so that's the cardinality of the vertex set. Okay, then the number of edges in a simple graph, right? Let's denote that number m. That's the number of edges. Okay, so this thing is going to be bounded from above by the following number. So this is n choose 2, all right? Okay, so that's the maximum number of edges you can have. It's like in a simple graph. Okay, and one other observation, if you will, is that every simple graph is a subgraph of sort of what is called the complete graph. So the observation is that every simple graph is a subgraph of the complete graph, which is denoted oftentimes by k sub n. Okay, well, I should say any simple graph with n vertices is a subgraph of the complete graph Kn. Okay, so what Kn is, as the name implies, is the set of n vertices. Let's just do 4 for now, where every time there is a pair of vertices, it's like there's a corresponding edge, right? So I connect sort of the all the possible, it's like pairs of edges here. So this is an example of K4, right? The complete graph with sort of all the edges filled in, okay? And you can check that, you know, it's like this 4 choose 2, right, is 4 times 3 divided by 2, right? So that is 6. Okay. So that's 1, 2, 3, 4, 5, 6. So there's 6 edges. So it's like, again, it's like you can check that that is indeed the complete graph with 4 vertices. Okay, so anyway, so it says that every simple graph is a subgraph of this complete graph, right? So you might ask, well, what does it mean? It's like for a graph to be a subgraph, right? So, right, G, let's say I have G bar, which is V bar, E bar, right, is a subgraph of G, which is V, E, right, if, right, so V has to be, as a set, has to be a subset, V bar is a subset of V, and E bar has to be a subset of E. All right, but that in and of itself is not enough. It's like it also has to be that G bar is a graph, which is to say that not only is E bar a subset of E, but that E bar, it's like consists only of edges which connect vertices in V bar. Okay. All right. So anyway, so that's the idea of a subgraph. All right. Yeah. And yeah. So anyhow, so the point in any case is that every simple graph, it's like you have, it's a subgraph of the complete graph with the same number of vertices. Okay, so we had this example of a graph which was simple, every simple graph, right? This is a graph which is simple. It's an easy to convince yourself that it is a subgraph of this, right? So here we haven't really, it's like done anything extremely interesting, because it's like in this particular case, it's like because you started with n vertices and you look at the Kn graph, right? So the number of vertices are the same. So in that case, V and V bar are, so V bar and V are the same. And the only difference is that you need that the edge sets, it's like our subsets. And then the graph condition, it's like automatically holds because you have all the vertices basically, right, in both of these cases. So here it's like it's easy to convince yourself that all the edges here are represented, it's like in the full sort of complete graph with n vertices. Okay, so that's a subgraph of this K4 graph. Okay, anyhow. So, so with that in mind, it's like the next question to ask is how, you know, can we make sense of the idea of connectedness? All right, and part of this idea is that there's a transitive property, right, which says that, you know, if A is connected to B and B is connected to C, then we oftentimes say that A is connected to C as well, right? So, so if this node, let's just again model this as A, B, and C, right? So if we have a vertex A connected to B, it's like by the existence of an edge, right? We also want to be able to say that B is connected to C, and also that B is connected to C, then it means that A is connected to C as well. Okay, all right. So maybe it's like, let me just remove this edge, it's like for now, right? So if A is connected to B and B is connected to C, we want to say that A is connected to C as well. So we want that this notion of connectivity between points, it's like in a space, is transitive, okay? So how do we make sense of that? So the way we do this is to introduce the idea of paths in this space. Okay, just erase everything. So in a simple graph, right, a path is just a sequence of vertices which connect two vertices, let's say u and v. Okay, so let's say u is u0, and then there's u1 all the way up to uk, and uk is the final vertex v. Okay, so we have a path which connects u and v. It's a sequence of vertices, u0 all the way up to uk. Okay, with the property that if you look at this pair ui plus 1, okay, that is in the edge set of the graph. Okay, when I is between 0 and k minus 1. Okay, so that's saying that there's edge u0, u1, u1, u2, all the way up to uk minus 1, uk. All right, so if I use this picture again, right, if this is u and this is v, right, this is a sequence u0, u1, u2, u3 with the property that every sort of sequential pair of vertices in that sort of path, right, is an edge. Okay. All right. And then the other thing it's like we can say about edges, or sorry, about paths, right, is the length of a path, right? So it's easy to convince yourself that the length of this path is like sk, right? So k is the length of the path. Okay, so 1, 2, 3, right? u0 to u3. Okay. Okay, so where are we? All right, so we have this idea of a path, but nowhere it's like in this definition of a path did we say that you couldn't repeat vertices in this. All right, so so the vertices in this sequence of in the path, right, can repeat, right? So the vertices can repeat. So you could either backtrack or you could sort of go in a loop, right? Can either backtrack or go in a loop. Okay, and that would still be a path. That's okay. But of course, it's like you might want to sort of get rid, it's like of all these redundant backtracking. It's like loops. It's like to have what is called a simple path. And as the name implies, it's like what happens in a simple path is that you have this sequence of vertices, but the vertices in that sequence are all distinct from each other. Okay, so a path without repeating vertices right is a simple path. Okay, and it's easy to convince yourself that if you give me a path, then I can construct a simple path out of that. Okay, all right. Okay, so now we have this idea of paths, right? We're in a position to talk about the idea of connectivity, okay, and whether or not a simple graph is connected. Okay, so let me define this for you. So definition: a simple path, a simple graph is connected Okay, so we say a simple graph is connected if there's a path between every pair of vertices, which is again what you might expect. Oh, sorry, every pair of vertices. Okay. All right. And then once you have that, it's like we can start talking about this idea of connected components. So say you have this, and then you have another part of the graph like this, then we might say that this is one connected component, and then this is another connected component, because these two are disjoint from each other. Okay, so so let me sort of say what a connected component is. So a connected component right, it's a maximal connected subgraph. Okay, so basically what I mean is that there's no way for me to add vertices. It's like from okay, so there's no way for me to have the property that this let me rephrase that. So a connected component basically is a subgraph. It's like of the original graph with the property that there's no other sort of subgraph. It's like of that. Okay, so maybe let's just say C. Okay, so C, if C is this connected component, right? So it's a subgraph of G with the property that this is connected. Okay, so if you say that it's maximal, that means that there does not exist some C prime, which is sort of inserted between these things, right? Such that C is contained in C prime, which is again contained in G, right? Where this is also connected, okay? And C is not is a strict subgraph of C prime, which is to say that C and C prime are distinct from each other. Okay, so so what that basically means is that you have to there's no way to add another edge or another vertex. It's like from the original graph, okay, while still keeping it connected. Okay, all right. So anyway, so this is what is called a connected component. It's like and it's this maximal connected subgraph. Okay. So with that, it's like we can talk about the idea of the smallest sort of connected graphs, if you will, right? So the smallest connected graphs are what are known as trees. Okay. So these are characterized by the property that there's always a unique simple path connecting any pair of nodes in a tree. And that any edge or removing any edge disconnects the graph. Okay. All right. So in fact, this, for example, is an example of a tree, right? You could have things like that as well. So the main idea, if you will, is that you can't have these paths which are closed, you know, in the graph if it's going to be a tree, right? So if you have if the existence of paths or non-trivial paths, if you will, it's like which are closed on each other, then this wouldn't be a tree. Okay, so with this idea of a tree, it's like there's a connection, if you will, it's like between trees, it's like, and this question of connectedness, and that's described in terms of what is called a spanning tree. So a spanning tree okay, of some graph G, right, is a tree with the same vertex set. So let's call it VT. Okay, and of course it's like the edges of the tree have to be a subset of the edges of the original graph. Then so T is a subset of E, and this whole thing is a tree. Okay. Right, as I said, it's like trees are by definition, it's like connected. All right. So anyway, so a spanning tree of this is basically some subgraph, if you will. It's like of the original graph. It's like which happens to be a tree. Okay. And then you can check that a spanning tree of graph exists if and only if the graph is connected. Okay. All right. So finally, it's like so we've talked about this idea of edges connecting. It's like vertices. We talked about the idea of expanding this notion of local connectivity to a more global notion of connectivity by introducing this idea of paths. Right? We have a characterization of whether or not a graph is path connected in a sense, right? By looking at the idea of trees and spanning trees. Okay, and then finally, it's like we want to be able to introduce the idea of separating. It's like disjoint components, if you will. Okay, so there is what is known as the idea of separation. So, all right. So a separation is a non-trivial partition of the vertices. So we start with this vertex set V, right? And want to write it as U union W, right? Where U and W are each non-empty, but their intersection is empty. Okay? Right, so U intersect W is the empty set. All right, and then so you have this non-trivial partition at the vertices. Again, non-trivial refers to the fact that neither of these things are empty sets. Okay, so because of course it's like you could always have written V as V union. It's like the empty set. It's like, and then this property would be satisfied. So that's why non-trivial is necessary there. Okay, and then all right. So we're not quite done yet. You have this, you have the vertex. It's like being sort of decomposed into two sets which are disjoint from each other, two vertex sets which are disjoint from each other, and then it has to be that there are no edges no edges in the original edge set E, right, that connects a vertex in U with a vertex in W. Okay. So again, that's sort of intuitively what we expect. So in this picture here, right, let's just get rid of all the labels, right? In this picture here, this piece here would be one component, if you will, and this piece would be another component. And if you let U be the set of vertices which are in this piece, and W be the set of vertices which are in this piece, right? And to convince yourself that on the one hand, these vertex subsets are disjoint from each other, but they together, it's like they give you, it's like the original vertex set with the property that there's no edge which connects vertices in one set with vertices in the other set. All right, so this would be a separation of that graph, for example. All right, so so it's sort of then easy to convince yourself that another way of thinking about the notion of connectivity, right, is that then a simple graph is connected, right, if there doesn't exist such a separation. Okay, so again, it's like this is sort of a simple idea. It's like about this idea of connectivity in the context of simple graphs. All right, and then subsequently we'll talk about what the analog of this concept of connectivity would be. It's like on a continuous space. All right, so let me just stop here for now.